Okay, so now we're over here doing the analysis, and now we are trying to do a quantitative analysis. So we want to understand what are the essential elements of a meta-analysis and when it's feasible and appropriate to do it. And then we want to talk about a couple of issues. As I said, most of the details are going to be reserved for tomorrow's class, but we want to talk about a forest plot, which is kind of the standard technique that's used to display the results of a meta-analysis. It's a nice visual graphic, and describe the different types of heterogeneity among studies and tools to quantify and explore heterogeneity. So again, this is going to be an overview. I'm not going to get into any sort of technical details today. So why do you want to do a meta-analysis? So the basic idea is you want to quantify the treatment effects and their uncertainty. So with a qualitative analysis, we're going to summarize what the studies were about, what they found, but we can't actually come up with a quantitative summary. I can't say, for example, and remember back to this morning when we were talking about the meta-analysis for cesarean section and maternal obesity, I was able to say that the odds of needing a C-section are 1.5 times higher if you are overweight. They were 2 times higher if you were severely overweight or obese, I guess, and 3 times higher if you were severely obese. That's quantifying the risk, right? It's 1.5 times higher, 2 times higher, 3 times higher. And I could also quantify the uncertainty by giving a confidence interval on that. So that's better than just saying it's worse. It actually says how much worse it is. And from that, of course, I can then make predictions and I can make extrapolations to how bad that effect is going to be in general. Another reason why you might want to do a meta-analysis is because you might have a couple of studies out there which are positive, but you might have a couple of other studies which are inconclusive or even negative, and you'd like to be able to put them all together. They're all small studies, and you'd like to be able to put them all together and come up with a final answer. Or another situation would be you have 4 or 5 small studies that are all trending in the same direction. They all seem to support the treatment, but none of them were big enough to definitively say there was a treatment effect. But you're hoping that by pooling them together, you can somehow increase the power. You can also increase the precision because obviously the more data you have, the more precision you're going to have in your estimate. Another reason is that you can explore differences between studies, not just qualitatively, but quantitatively. You can say, for example, that this effect is bigger in obese women than in overweight women, or this effect is different in men than in women. And finally, you can possibly use it to generate new hypotheses. So you might be able to say, for example, it looks like this treatment works in this particular type of individual, not in this particular type of individual. So these are all reasons to potentially do a meta-analysis and to try to quantify these effects. So when can you do a meta-analysis? Well, technically, you can always do a meta-analysis when you have more than one study, because you're just combining studies together. As long as there's more than one, you can combine them. However, with 2 studies, you're not going to have much possibility of looking at uncertainty, because a meta-analysis, the sample size in a meta-analysis is the number of studies. And so if you have 2 studies, your sample size is 2. And as you know, you can compute things with 2 studies, but you're not going to get a very accurate estimate. The studies should be sufficiently similar to produce a meaningful and useful result. What that means is that if I'm going to summarize the data, and right now I'm just sort of talking about an overall average, if I'm going to combine all these studies and come up with an overall average and say the effect is this, then that needs to actually apply to something. Like, what are those studies that actually give me this result? So if I say that overweight women are 1.5 times more likely to need a C-section, then that means that's got to apply to some set of studies that actually are combinable in some sense, right? So what kinds of study, what kind of women, what kinds of, for example, if they're using different procedures, if they're using women of different gestational ages, if they're using, or babies of different gestational ages, if they're using women with different age categories, like, for example, one study is looking at older women, one study is looking at younger women, then I might have confounding there, right? It might be that most of this result is driven by the fact that older women are more likely to need a C-section than younger women, for example. And it might just be that the older women are more heavy. Again, there's got to be some sort of similarity in the studies. The outcome has to be measured in similar ways. So again, a C-section is a pretty definable outcome, but there's a lot of other outcomes where, for example, it might be a rating scale, and those scales are defined somewhat subjectively. And then finally, of course, the data have to be available in a format we can actually use. We need the means, we need the standard deviations, we need the sample sizes for that kind of analysis, or we need counts and so forth. Okay, so to combine or not to combine is the question. And so there's this old sort of apples and oranges, but are they fruit? And so some people would say, well, combine them, they're both fruit. Other people would say, well, they're different types of fruit, so we shouldn't combine them. So again, this is a subjective question, right? There's not really like a tried answer in terms of whether these things should or can be combined. So we're going to look at different ways of doing a meta-analysis, and our analytic plan here depends on the aim of the review. So if we were interested in obtaining an effect size from similar studies that are estimating the same effect in the same kind of population and so forth, we use what's called a pairwise meta-analysis. And the pairwise meta-analysis here is comparing two things. So we want to compare, let's say, an intervention and control, and we're going to do a meta-analysis that's basically going to average the differential effects that we found between the intervention and the control in all the different studies. If we're interested in multiple interventions and comparators for the same condition, so we have not just an intervention and control, but we have several treatments. For example, we're interested in comparing all the different types of antidepressants of a certain class to see how well they control depression. Then we will do what's called a network meta-analysis. And so I'll say a little bit more about that tomorrow. That's becoming a very popular technique these days. The idea is that the studies kind of form a network, and you make all pairwise comparisons between all sets of treatments. If you're interested in investigating the relationship between the size of the effect and some study characteristic, for example, I could have put all of the C-section studies together and categorized the women in the studies as being overweight, severely overweight, or obese. And I could then have done a regression analysis to see what the difference between all those is. Then I'm doing what's called a meta-regression. And there's other aims you might have as well, depending on what you're interested in. For example, in diagnostic tests, we look at sensitivity and specificity and so forth. All right, so what are some of the study types that we can combine? So typically, the data that we have are going to be either binary or categorical. In other words, the outcomes can be classified into categories. And in that case, our main analyses are going to be proportions, odds ratios, risk differences. And so we would be combining those together. So we might be averaging the odds ratios, averaging the risk ratios, averaging the risk differences, and so forth. If the data are continuous, if we have continuous outcomes, then we're talking about means, and we would be combining means, or we might have correlations. We have correlational data, or mean differences, or standardized mean differences. Again, I'll say more about these tomorrow. If the outcome is a time to event, then we might be combining survival probabilities, median survival times, or hazard ratios. If the data are counts, we might be combining incidence rates or incidence rate ratios. If the data are diagnostic test accuracy, we might be combining sensitivity or specificity, or predictive value, or odds ratios, or ROC curve areas. So these are all different. All of these types of summaries can be combined through meta-analysis. So typically, the outcome in meta-analysis might be a summary, right? It's not just, the outcome in a study might be the change in blood pressure, but the meta-analysis outcome is the difference in the mean blood pressures between two groups. Or the outcome might be whether somebody lived or died, but in the meta-analysis, the outcome might be what's the average odds ratio of death compared to some outcome. And we have two different types of data sources. So we've talked a lot about summary study data here, where you go and you collect data from different papers, and you extract the data, and you extract all of these summary measures. But we also have talked a little bit about individual participant data, where you might have the raw data from all the studies, and you go and you combine all the databases together and try to do a reanalysis of those. So again, those are both common in the literature. So the first thing you want to think about is what's the effect that you're trying to measure. And so we might be looking at various types of effect in a given systematic review. For example, the most common use of meta-analysis is to look at the effect of interventions. So how does one intervention compare to another? We might also be interested in the association between an exposure and an outcome. So this might be some sort of a regression analysis where we're looking at a slope. And for example, for every increase of 1 unit of some exposure, the outcome increases by a certain amount. And so that's slope, some sort of a beta coefficient or regression coefficient. So you might want to combine those together across different studies. Or you might be interested in prevalence or incidence. What is the proportion of people who have a certain type of condition? Or what are the what's the average passing rate on a certain test? Or how many what proportion of animals in a certain field are mammals? Or what proportion of sewage is coming from residential households? And those are some certain kinds of questions you might be interested in coming up with an average of. Or diagnostic test accuracy. If I give somebody an X-ray, how likely is it that it's going to properly, and the radiologist will properly come up with the right diagnosis? Or if I'm testing a pregnant woman for trisomy 21, which leads to Down syndrome, how accurate is the ultrasound test, for example? How sensitive it is, how specific is it, how many false positives, how many false negatives? So these are often called effect sizes or effect measures or measures of association. And we typically use different measures depending on the type of data. All right? So again, in meta-analysis, the outcome is this difference. Whereas in a regular analysis, the outcome is something we're interested in measuring, and we would calculate the difference as our statistic. Meta-analysis is basically using the statistics as the outcomes. All right, so let me give you a very simple example here. I will repeat tomorrow, but let's say we have 3 studies, and these 3 studies are measuring some continuous or quantitative outcome. Let's say it's a difference in means. And in the first study, the difference in means is 6.2 in favor, let's say, of the treatment. It reduces something by 6.2. Let's say it's blood pressure. If the average blood pressure is 6.2 less in the treatment group than in the control group. In the second study, the difference is 7.7, and you see the confidence intervals in those studies. So both of those studies would be positive studies, right? They'd say that the treatment works. The confidence interval doesn't include 0. The treatment is giving you a reasonably large effect. The third study, however, is coming up with not only a non-significant result, but also basically a null result because the estimate is pretty close to 0. All right, so my question is, if I told you that these were the 3 studies that were available on a certain technique that was reducing blood pressure, and I asked you the question, does this technique work or not, what would you conclude? All right, so the qualitative answer is that 2 of the studies showed a significant improvement and 1 didn't. Another way of stating that, which is a little stronger, is that 2 studies showed a significant improvement and 1 showed no improvement. And the reason I can say that is because, well, the estimate is close to 0, although the confidence interval is fairly wide, right? So somebody might say, well, 2 out of 3 studies are positive, and so therefore this treatment works. Somebody else might say, but it didn't work in that other population, so maybe there's some heterogeneity there. All right, so what I'm interested in is an overall answer. So what do you think? What are some ways that I could combine the data there? By sample size, meaning how would I combine by sample size? So a weighted average, right? Okay, so so the first way is actually the easiest way, is just to take an unweighted average, right? It's just to say, okay, I'm just going to average the 3 effects together, the 6, the 7, and the 0, and my average is minus 4.7, and I can calculate a variance for that, and I can get a confidence interval. And so if I weight all these studies equally, then the true effect, or the estimated average effect, is minus 4.7, and the 95% confidence interval includes 0, so therefore it's not significant, and therefore I can't conclude that these treatments work. All right, so if I presented that analysis to you, let's say I just showed you the data and I presented that analysis, and I didn't tell you how I did it, would you believe the analysis? So it'd be kind of hard to tell because you didn't really know what I did. You might be able to figure it out. So what's the advance? What are you assuming if you give all these studies equal weight? They have the same amount of information. That basically they're equally likely to give me the right answer. And therefore, since I don't really know one study any different from the other, I'm just going to take an overall average of them. Now, the problem is that, of course, the answer that I get by doing that is somewhat at odds with two of the studies that I found. And it agrees with the third study. So let's try a different way. This time, let's weight by the sample sizes, right, which somebody suggested already. So now I'm going to give, basically, I total all of the sample sizes, which comes to 897. And so I weight the first study by the fraction of the data that are in that study, which is 554 out of 897. And then I weight the second study by 300 out of 897 and the third study, and so forth. And now I get an estimate that's much closer to the first two studies because they were the big studies and they got most of the weight, right? So now I have a bigger effect and it's significant, right? Because basically it's kind of just averaging the first two studies and basically excluding the third one because it's such a small weight. Okay, so now, do you believe this study more? This result? Okay, so some of you are nodding your heads, and that's presumably because we all kind of believe the bigger studies more than the smaller studies, right? Which is not an unreasonable assumption. However, playing the devil's advocate, I could say, well, the third study was done in Japan, and the other two studies were done, let's say, in Europe. And so therefore, maybe the reason they're different is that because this intervention was used differently in Japan than it was in Europe. Maybe it had a different, it was manufactured differently, or maybe it was, maybe people from those countries react to this in a different way, right? So maybe there's heterogeneity here. That would argue for not giving one answer, right? That one average not being really the right answer. Okay. So that's the basic idea behind meta-analysis. And so you can see already that there's a lot of room for kind of subjectivity here in the sense of like, what weight do I use? So there's a couple of different ways of thinking about the way we weight these analyses. And so I'm going to give you two different graphics here. Let's say that the rows here are the studies, and there are 4 studies that use the blue treatment and 4 studies that use the red treatment. So one way that I could pull these data together is I could average up all the effects in the blue studies and all the effects in the red studies and take the difference, and I get the green box on the left. All right, so I'm averaging over the studies within each group. I'm going to compare the averages across the groups, and I get this estimate. So that's one way of doing it. The other way of doing it is I can, in each study, compare the red with the blue, and then I average the differences. Okay, this is actually the way it's done in meta-analysis, right? And these will oftentimes give you different answers. The epidemiologic or statistical phenomenon is called Simpson's paradox that some of you might have heard about. And basically, it's because of the different ways things are weighted. The reason that this approach is preferred in meta-analysis is because, let's say these studies were randomized, or at least they were, the groups were supposed to be comparable at baseline. Then this comparison here is a valid comparison for that study, and therefore this estimate here is a valid estimate of the difference between these two groups. So is this one, so is this one, so is this one. And so therefore, by averaging them, I'm averaging 4 valid estimates, right? Here, I'm combining 4 things across studies that might be completely different. And I'm combining 4 things here that are completely different. So there's nothing that says these 2 things are comparable, right? Let's say that, for example, the blue is actually worse than the red, but actually you have a lot more people in the blue group here than in the red group, and here you have a lot more people in the red group than the blue group, so things might be confounded. So this is actually the way we do meta-analysis, is we calculate the effect in each study, and then we combine across the studies. Now, the reason that that's nice for meta-analysis is because if I do the analysis this way, I only need the summary study reports that give me these study effects. Right? I can, as long as you give me the mean difference in each study, I can calculate the average. Over here, I'm going to need the individual data in each treatment arm to be able to calculate this. So this might be more amenable to pooling across studies. So it's useful in a couple of different ways. All right, so let's just as a quick review, yeah. Mm-hmm. So, oh, here, you mean? Well, it's just, let's say these have been randomized to these two groups. This is, let's say, an control group, and this is an intervention group. So in this study, this is the result for the people in the intervention, and this, or control, and this is the result for the people in the intervention. And I'm just taking the difference between the two.
Like in the first and second row, what pairs, why are we pairing the first one is relative? And what is the nature? What do those two in the same row have paralyzed?
They're the same study. These are the studies. This is study 1, study 2, study 3, study 4.
Oh, you're looking at the control and
intervention. Yeah. So the rows are the studies, and the columns are the groups. Okay. All right. So let's just a quick review. Let's say we had binary data. So now we have a test and a comparison, and each group we either have an event or no event, right? So it's 2x2 data, and so we have these counts A, B, C, and D. And so NT is the number of people who got tested, and NC is the number in the control. And so what we're interested in here is different ways of looking at this comparison between these two groups. So the first one is the risk ratio, which says basically what's the rate of events in the test group compared to the rate of events in the control group. And so that's the rate of events in the test group is A over NT, and the rate of events in the control group is C over NC. And we take the ratio of those two, and that's called the risk ratio. Right? The odds ratio says what's the ratio of the odds. So the odds are the number of events divided by the number of non-events. So those are the odds of having an event in that test group, and this is the odds of having an event in the control comparison group, and the ratio of those odds is the odds ratio. And then the final way is the risk difference, which says the event rate in the test group is A over NT, the event rate in the comparison group is C over NC, and the difference between those is the risk difference. So all three of those are common ways of describing binary data. Now, remember when we're doing meta-analysis, our outcome is the effect measure. So the outcome is actually either the risk ratio, the odds ratio, or the risk difference. So there's 3 different ways of doing the meta-analysis here, depending on which metric I want to use to do the combination. I can combine the risk ratios, I can combine the odds ratios, or I can combine the risk differences. And now that will definitely give me different answers. There's another way, which is you'll sometimes see in the literature called the number needed to treat, which is basically just the inverse of the risk difference. And the reason it's called that is because let's say that the intervention cures 10% of the people and the control cures 5% of the people. So the difference is 5%. That means 1 out of every 20 people, more people are being cured in the intervention group than in the control group. That means that I need to treat 20 people to cure 1. Right? So every 20 people, I'll cure 1 more person in the intervention group. That's why it's the number needed to treat is 1 over the risk difference. Okay, so to do the meta-analysis, what are the data that you need? You either need the total numbers of people in each arm and the number with the outcome in each arm. In other words, I need either A and NT or C and NC, or conversely, I need the 4 numbers of this table. Or I need the effect measure with a confidence interval for the study. In other words, I need the odds ratio, the risk ratio, or the risk difference together with its confidence interval. If I have the 4 numbers, I can compute these things, and then I can do my analysis. If I'm just given one of these, then I can only do that in particular analysis. All right, so that's for binary data. For continuous data, we typically have means. So we'll get the mean in one group and the mean in another group. And so we want to look at the mean difference is typically the way we would analyze this. We could also look at a ratio of means, but it's more common to look at a difference. But sometimes we might use a standardized mean difference, which is the difference in the means divided by the standard deviation, let's say in the control group. Now, why would you do that? Well, you might do that because you might have 2 means in your 2 groups in your studies, but those means might be on different scales. So for example, one is using one depression scale, one is using another depression scale. These are different scales. So the differences in the means are not comparable because they're different scales. But if you scale them by their standard deviations, the differences in the means are now relative to their standard deviation. So now they're standardized units. And so the thought is that you can combine the standardized. So for continuous outcomes, you need either the total numbers in each arm of the study and the mean in each arm of the study, and the standard deviation, or a way to calculate the standard deviation in each arm, or you need the effect measure, like the mean difference, with its standard deviation or confidence interval. And from that, you can then calculate what you need to. All right, so now let's look at a forest plot. So the forest plot is the standard kind of picture that you often see in meta-analysis. So this is a forest plot coming from a paper that was published many years ago on looking at the effect of beta blockers for preventing new heart attacks. So I'm going to go through the parts of this forest plot here. So the first thing is you'll notice that on the bottom, it's fairly small type there, but that's an odds ratio scale, and it's on a log scale. So to the right are numbers greater than 1, and to the left are numbers less than 1 of the vertical line. So that's the line of no effect at odds ratio of 1. If the odds ratio, so this is the odds ratio of the rate of events of heart attacks in the beta blocker group compared to the control. So if the odds ratio is greater than 1, that means that there's more events in the beta blocker group. And if their odds ratio is less than 1, it means that there's fewer events in the beta blocker group. So therefore, things over here favor the beta blocker and things over here favor the control, right? And here's the line of no effect. So here's the beta blockers and here's the control. So if we look at a given study, let's say this study here, this dot or square indicates what was the odds ratio that was calculated in that study from those studies' data. And so it lines up at about an odds ratio of let's say 7 or 0.6. All right, so that was the estimated odds ratio in that study. And this line is the 95% confidence interval line, and it stretches from an odds ratio of about 0.2 to an odds ratio of about 1.5. All right, so that was the 95% confidence interval. Notice that that line overlaps the line of no effect. So that tells you that that study was not statistically significant. Even though it had a fairly big effect, right? The effect is fairly big. It reduced the beta blocker by, reduced the heart attack risk by about an odds of 0.4 to an odds ratio of 0.6. In other words, about a 40% reduction, but it's not significant. Now let's look at another study. Let's look at this study here. This study here also has a pretty big effect, but notice that it is statistically significant, right? Because it's completely to the left of this line. So if we look at this total plot, this gives us a sense of kind of where each study fell, right? And what you can see is that most of the dots, of the squares, are to the left of the null line. In other words, most of the studies favored the beta blocker. But you can also see that most of the studies they cross the null line. So most of the studies were not significant. There are a few that are. Let's see, so this one is, and this one is, and this one is, and this one was. So we have, and this one. So we have 5 positive studies in favor of beta blockers. There are no studies that are favoring the control. And then we have about 20 or so inconclusive ones, right? So we want to summarize the data. So before we go any further, just thinking about what I said, do you think the beta blockers work or they don't work? They work. Why? Okay. So the majority of studies show a positive effect. All the studies that are statistically significant are favoring beta blockers. There's none favoring the other. These are all sort of qualitative conclusions though, right? So, I mean, that's all reasonable, but somebody might argue another way and say, yeah, but 80% of the studies were inconclusive. So therefore, how can you conclude that there's a positive effect here? We also, by that, we can't tell how big the effect is. If I wanted to know, how much of a reduction is it? Because maybe, for example, the beta blocker is a much more expensive treatment than the control. So is it worth paying for? If the reduction's only 1%, it might not be worth paying for. If the reduction's 30%, it might be worth paying for, right? So how big is the effect? So this is our meta-analytic answer, which I'm not going to tell you exactly how to compute, but it's just a weighted average like we were talking about, right? So this dotted red line indicates the average meta-analytic effect across all these studies. It's 0.77. So that says it reduces the risk, the odds of a heart attack by 23%, right? And the width of the diamond is the confidence interval on that summary effect. And so that's pretty tight. That's between about 0.7 something and 0.82, or it's very tight. It's statistically significant because it doesn't include the null value. And so we're pretty sure that this effect is around 20, 25%. Okay, that's what the meta-analysis tells us. So by averaging all these things together, we have come up with this answer. All right, so I don't think most people would complain about that answer. The point estimate is in the middle of all the dots. It's fairly strong evidence, but then we know that 5 of the studies were significant and there were none negative, and there were 20 inconclusive, but most of those were on the right side of the line. So that's probably a reasonable estimate. All right, so that's how the meta-analysis would be done in that case. Yes?
I don't know what you did, but I'm just why you would have so much variation in each study, and then your meta-analysis doesn't reflect that.
Okay, so right. Okay, so that's an important feature of the fact that I'm estimating the mean, right? So I'm estimating the mean effect of these studies. So typically the mean is estimated much more precisely than any individual observation, right? So if I, okay, so height is a good example. If I asked you what is the average height of, let's say, a woman in the United States, and you said, okay, 5'8", and I said, okay, so what kind of variability might I expect in an individual woman? You might say, well, most women are between, let's say, 5 feet and 6'2", right? So that's a fairly wide range. If I now ask you the question, what if I took a sample of 100 women and I calculated the mean, and I did that again, and I did that again, and I did that a bunch of times. I took 100 samples of 100 women. What would be the variability in their means? It'd be much smaller, right? Because the mean is going to have much less variability than an individual item. So the mean is going to be close to 5'8" in each of those 100 samples. And so therefore, most of the means are going to be near 5'8". They're not going to be between 5 and 6.2. So 6.2. What I've done here is I've said, what I'm calculating is the overall average effect. So in other words, what I'm interested in is the variability here of the means rather than the variability of the individual studies. So these means are pretty tightly grouped around 0.77. I only have 1 or 2 that are to the right of 1, and I only have a couple that are below 0.5. So I'm pretty sure what that mean average is. Okay. All right, so now the next thing we want to think about, oh, yes?
So if you were to combine all of those into one study and look at that mean would be very different from what you just calculated.
Right, if I wanted to actually predict what the next result in the next study was, that's what we call a predictive interval, and that would be wider because now I would have to consider not just how well I know the mean, but how well I know an individual study. Yeah, we'll get into that tomorrow. Okay, so so we've talked about the average. Okay, so the next question is, what about the heterogeneity? So think about a hypothetical population made up of subgroups. And so all these little curves there are different populations. And I construct a set of a set of studies, let's say N studies, and each of these studies is drawing from some of these subpopulations, right? So let's say this is people in the United States, this is people in Europe, this is women, this is men, and so forth. So some of these populations go into some of these trials. Not all the same subgroups will go into the same trials. Now I'm going to combine these results into a meta-analysis. So what happens is that I now no longer have a representative sample of this whole population. I have whatever I observed in these studies. And so that's why I'm getting heterogeneity here, because this study's results are different from this study's because they're sampling different people. And to the effect that there's differential effects in these subgroups, therefore I'm going to get differential effects in these studies. And therefore, when I combine the meta-analysis, some of the subpopulations will be overrepresented, some will be underrepresented. And I'm hoping that the average will be close to the true average. But I can't be sure of that. So there's different subgroups here are representing various patient characteristics and disease manifestations, and they may have different responses to a treatment. There's different inclusion criteria, different patient recruitment methods, different random variation in study, and this can lead to cohorts here in these studies that are consisting of different distributions and combinations. And then when you combine these studies into a meta-analysis, the way these studies are constructed, they're going to have different protocols, different study designs, different ways of reporting, different types of biases, and that can also affect what you see in the meta-analysis. So for example, let's say these N studies were done, but this second study was never published, I would never see it, right? So it wouldn't come into my meta-analysis. So I would get, this would be, so interpreting the results of the meta-analysis of these trials depends on how the data are synthesized, and we could do this in various ways, and we try to adjust for the way these things are sampled, but we really don't know how those studies are being sampled. So there's always some sort of measurement of idea of uncertainty there. So how do we deal with this heterogeneity? So we have heterogeneous treatment effects. We saw that in the beta blocker example. Some of the studies were positive, some were negative. What do we do? Okay, so one thing we can do is just ignore it. And so we can use what's often called a fixed effects or a common effects model. We ignore the uncertainty and we just go ahead and report the average and say, well, I don't care about the uncertainty. Here's what the average is. And you apply it to everybody or to every study. The second way that you can deal with it is you can try to model it. And so we'll talk tomorrow about what's called a random effects model. And in that model, you allow all of the studies to have potentially different effects, but they're all drawn from the same sort of distribution of effects. And so there is an overall average, but it's applying to the distribution of effects, not to any one particular study. A third way is you could try to estimate the heterogeneity there is there. And if you find heterogeneity, just say, well, I'm not willing to group the data together because I don't know what the average means. And then a fourth way is you could try to actually explain the heterogeneity by using some sort of subgroup or regression analysis. So again, we'll talk about all of these tomorrow. So here's another example. This is an old meta-analysis that was done looking at thrombolytic therapy for treating heart attacks. Thrombolytics are clot busting drugs. When you have a clot in your arteries, they can break apart the clot and clear the blood apart. And this is what's called a cumulative meta-analysis because the studies here are ordered in chronological order. Sorry, they could be ordered in chronological order. In this case, they're going to be ordered in another way. This is the forest plot. This is a little bit hard to read, but here's the line of no effect. You can see that most of the studies are to the left of it, which shows that these treatments are effective. But notice that if you look down these, dots, these dots are much further to the left of the null line than these ones are. And in fact, if you accumulate the results of these studies in this order of these studies, you can see that there's a pattern here, and it's that you get the biggest effects here, and then as you go along, the overall effect is getting smaller and smaller. And that's because these are ordered in such a way that the effects are bigger here than they are here. All right, so I've accumulated them in that way. Now, what's causing that? So if I look at those studies, and I compare them to those studies, here's what we call a variable or a covariate. This is the mean time to treatment. And so this is 0.7, and this goes down to 3, and this goes from 3, 5. So in these studies, everybody was treated within 3 hours of their heart attack starting. In these studies, the mean time to treatment in those studies was between 0.7 and 3 hours, right? So in other words, in this study, on average, people got their treatment within 3/4 of an hour of their first symptoms. In this study, the average person got them within 3 hours of their first symptoms. These studies all are getting the treatment between 3 and 5 hours. These are all between 5 and 10 hours, and these are more than 10 hours. Now, if you look at the dots here, you'll see that these are much bigger effects than these. And then this continues to trend this way. These are bigger than these, are bigger than those, are bigger than those. When we put them all together, we find that the treatment is much more effective if it's given quickly. And here's the estimate. So if we just combine the 0 to 3 hour studies, we get an odds ratio of 0.7. In other words, the odds of a heart attack are reduced by 30%. Or sorry, the odds of dying from a heart attack are reduced by 30% if I give the treatment within 3 hours on average. If I give it between 3 and 5 hours, the odds are reduced by about 20%. If I give it within 5 to 10 hours, it's about 10%. If I give it more than 10 hours, it's about 5%. And the overall average is around 25%. So here, if I reported the overall average, I would be saying that if I give this treatment to people who are having a heart attack, on average, I can save about 25% of them, right? Or I can at least reduce their odds of dying by 25%. However, you can see that this is a much more effective treatment if given early than if given late. In fact, this is not even significant. And so it indicates that if you come in really late, this treatment might not be very effective. So if you are a policymaker who's trying to figure out for whom you should pay for these drugs, you might say, well, make sure that these people are treated, and if you have enough left over, you can treat these people, but otherwise, if you've got a choice between this person and that person, it's much more likely that that person's going to be helped by it. All right, so that's one way of thinking about it. Another way of thinking about it is that we need to get these people to the hospital really much more quickly than we're getting them, right? So that you can actually save. Yes, question. Well, in this case, probably what it's done is there was just, first of all, there was probably some expert opinion, but secondly, you could just do this as a regression analysis. You might just have noted that those studies which had a quick time to treatment seemed to have better effects, and so then you might have, yeah, you could just do that as a regression. So another way of thinking about this is just to plot the odds ratios versus the time to treatment, and you see this trend. Okay. So again, this is a quick overview of sort of two of the things that we do in meta-analysis. One is we calculate the average effects, and the other we look at heterogeneity. So the meta-analysis gives you a statistical summary of effects from different studies, usually based on some sort of statistical model. We will talk about those more tomorrow. The most common summary in a meta-analysis is a weighted average. And actually, they should say the forest plot, not the funnel plot. The funnel plot is another type of plot, which I haven't talked about. The forest plot displays the study summary results in one picture that can aid in interpreting results. For heterogeneity, study results vary because of different objectives, designs, and analyses. If you explore heterogeneity, it can illuminate reasons why results differ, thus enhancing scientific understanding. So, an example we gave, we learned that not just that these thrombolytic drugs work, but that they work much better if you give them quickly, and therefore the scientific conclusion is we need to get people treated more quickly. And that's actually one of the pushes that has been made in the last 30 years or so for trying to inform people about what are the symptoms of a heart attack so that they know to go to the hospital quickly. Various graphics and statistics are useful in quantifying between study heterogeneity. And we can't really solve heterogeneity if the studies are truly diverse, because then it might just be better not to combine them at all. Or we might not have enough data. So we were lucky in our example here to have a lot of studies. And so we were able to come up with some sort of a summary of these into subgroups. But if we had only had 4 or 5 studies, then probably we wouldn't have been able to summarize things that way, because we might have only had one in each group, and then we wouldn't really have known whether that effect was true. Yes. Yeah, I mean, I would say, so again, if you treated this as a continuous type of covariate, so you were looking at time as a continuous variable, then you probably only need 5 to 10 studies. Just think of it like a regression. What's the sample size you need for a regression? If you're looking at it really in subgroups, like these were really different types of interventions, then you'd probably need several in each group to estimate it well. Okay. Any other questions on meta-analysis? So yes. Yeah, I mean, this wasn't my analysis, so I don't really know what caused these guys. I suspect that what happened was that, they had all these data, and somebody had noted that the studies that, well, okay, remember these studies were done between 1959 and 1990. So there's 30 years of data here. So people have been thinking about this a long time. Some of these studies are very well known, and so people knew that the studies, they knew there were differences, and people were speculating, is it this, is it that? And so, from basic science and from lots of things, that probably came up with this hypothesis that the time to treatment was really important. And then they tested that out here. Somebody might have actually tested it out before, and they just did it with all the data. So, remember, meta-analysis is not really causal in the sense that these are really observational data, right? This is not a randomized experiment. This is just, you're collecting the data you have, and you're trying to look at patterns. Okay, module 9. So this is our last module of the day, unbelievably. I really never thought we'd get here. We might even finish early. So now you've done all this stuff. Now, what do you actually tell people at the end? All right, so reporting your findings. This is this book you're writing. It could be just a paper. It could be your dissertation. Could be a lot of things. All right, so first I wanted to say a little bit about the process. So, I talked a little bit this morning about Abstractor, which is a semi-automated abstract screening tool. And there's several other tools like that. A couple of people asked me over the break about them. So there are various tools around here, and they're not just tools for abstract screening using automation. They're also tools for extracting data, right? So people are using natural language processing, machine learning, and so forth to figure out, where the key pieces of information are in these papers, and to try to automate this type of extraction. We've actually set up an add-on to the SRDR program that enables you to display, if you have 2 reviewers, if you can take the data extraction form and place it side by side with the PDF of the paper, and you can, for example, if one of the questions in the extraction form is what's the average age of participants in the study, and you find that in the paper, you can actually drop a hot link on it so that the 2 link together. So if somebody's checking your work, they can say, oh, okay, this is where you got that information from. And so that's very, we tested that out. Unfortunately, it didn't really improve our results. I mean, we didn't have fewer errors that way, but at least it documents the process. And so I think things like that will become increasingly more important. And then the natural language processing is very useful for pulling information out. It's a very difficult problem. For example, even if something as simple as was the study a randomized controlled trial, the word randomized controlled trial may never actually appear in the document, or it might appear in a couple of different ways. For example, in one part of the paper, it might say the patients were randomized. In another part of the paper, maybe the introduction, it might say there are many non-randomized studies of this technique out there, but we're not actually interested in those. And so, the computer doesn't necessarily know very easily, which is a positive statement and which is a negative statement. So there's a lot of computer scientists kind of working on this problem. So there's different platforms out there that are being developed. The other thing is the meta-analysis itself. We've actually been working for years on a tool which exists, and a lot of people have used it. What we've been trying to, what our idea was in the beginning was that many of the sort of standalone meta-analysis packages that have sort of a point-and-click interface for people who are not really skilled with programming don't really have a lot of the important features that you need. They don't do some of the sophisticated models. Whereas these models are available in software like R, which are much harder to use, right? So if you know how to program, you have all this flexibility, but if you don't know how to program, you don't. And so what we've been trying to do is to build an interface on top of the R so that you could go either way, basically. You could choose your analysis and do whatever R can do. And so there are a few of these programs out there. Stata is another program that actually has a lot of good meta-analytic routines, and people have been developing good software for that. So I'll say more about this tomorrow, but just to say that this process is becoming more and more automated. So we have Extractor here. We have SRDR, which is a platform for extracting and archiving the data. And then our program is called OpenMeta or Open MetaAnalysis. All these you can download from our website. The Open MetaAnalysis is actually being revised to have a web interface. It's currently a standalone program, but you need to have either a Windows or a Mac version, and we don't always keep them up to date. So we're trying to put that over to the web. All right, so now we're going to get to reporting. So a couple times I've mentioned this PRISM statement, and here's the answer to your question, Larry, about where the definition is, what the name is. It's the preferred reporting items for systematic reviews and meta-analyses, and it's a 27-item checklist. And if you Google the Equator Network, you'll see a lot of different checklists for different types of studies, whether they be meta-analyses or regular studies or whatever. So they've collected all these checklists at this network. And here is the checklist. This is the 2009 checklist, which I think was an update of an earlier one. And so let me just go over these fairly quickly. So the first thing, these are things that should be included in a meta-analysis that you write up. So the first thing is the title and the checklist item. So this statement comes along with a long explanation and elaboration document that you can also download. It will tell you basically all the details of the items, but the item itself can be described pretty simply. So identify the report as a systematic review, meta-analysis, or both. So this is something that's very useful for indexing and for finding. So typically these days, when you see a meta-analysis in one of the major journals, it might say the efficacy. Let's say the efficacy of the efficacy of omega-3 fatty acids for cardiovascular disease, a meta-analysis, or a systematic review, or something, just to identify that should be in the title. I don't know if that's as common in other fields, but this is something that at least in the medical literature and the clinical literature is recommended. The second thing is in the abstract, they recommend a structured summary, which means that you don't just want a paragraph. You want a paragraph. You want to have an abstract that has different divisions. For example, it might have background, methods, results, conclusions, and so forth. Provide a structured summary including the background, the objectives, the data sources, the study eligibility criteria, participants and interventions, study appraisal and synthesis methods, results, limitations, conclusions, and implications of key findings, systematic review registration number, all this in 250 words or less. But they're often very cryptic. The background might be, many patients are at risk of stroke, and then the objective might be to determine whether X treatment reduces the risk of stroke. And then the data sources are data, randomized controlled trials conducted between 1990 and 2015. And then the study eligibility criteria might be all, randomized controlled trials with, something and something and so forth, and interventions, and they'll list those. Then in the introduction section, you want to describe the rationale for the review in the context of what is already known, and provide an explicit statement of questions being addressed with reference to participants' interventions, comparisons, outcomes, study design, PICOs. So this is much like any scientific paper, right? What goes in the introduction is why you're doing the study. But then they want these explicit objectives to relate them back to these structured items. Then in the methods, you would provide the protocol and the registration. So if you've registered this, it's something like Prospero, or where somebody can find the protocol for the review itself. The eligibility criteria, what kinds of studies are allowed into your review, and why. Your information sources, so all the databases you use, the dates that you search them on, any contact you had with study authors to identify additional studies and in the search, and the date last searched. The search itself presents a full electronic search strategy for at least one database, including any limits used such that it could be repeated. The study selection state the process for selecting studies, i.e. screening, eligibility, included in the review, and if applicable, included in the meta-analysis. The data collection process describe the method of data extraction from reports, e.g. did you use piloted forms, did you extract independently and duplicate, and any processes for obtaining and confirming data from investigators, like did you call them up and ask for missing items. The data items list and define all the variables for which data were sought, e.g. PICOs, funding sources, and any assumptions and simplifications made. Risk of bias in individual studies describe the methods used for assessing the risk of bias, including specification of whether this was done at the study or outcome level and how this information is used in any data synthesis. Then the summary measures state the principal summary measures, e.g. risk ratio, difference in means. The synthesis of results describe the methods of handling data and combining results of studies if done, including measures of consistency, e.g. I-squared for each meta-analysis. Again, we'll talk about those more tomorrow. Now, risk of bias across studies. So there's risk of bias within studies. Now, across studies specify any assessment of risk of bias that may affect the cumulative evidence, e.g. publication bias, selective reporting within studies. Additional analyses describe methods of additional analyses, e.g. sensitivity or subgroup analyses, meta-regression if done, including which were pre-specified. Okay, so that's all your methods, right? That should all be specified so that somebody can basically reproduce your results. And now in your results, you want to give the numbers of studies screened, assessed for eligibility. That's that flow chart included in the review with reasons for exclusions at each stage, ideally with a flow diagram. Study characteristics for each study present the characteristics for which the data were extracted. For example, the study size, the PICOs, elements, the follow-up period, and provide the citations. The risk of bias within studies present data on risk of bias, and if available, any outcome level assessment. The results of individual studies for all outcomes considered, benefits or harms present for each study, the simple summary data for each intervention group, and effect estimates and confidence intervals, ideally with a forest plot. The synthesis of results, you want to present the results of each meta-analysis done, including confidence intervals and measures of consistency. The risk of bias across studies is you want to present results of any assessment of risk of bias across studies, and additional analyses give results of any additional analyses, subgroup sensitivity and meta-regression. Okay, then once you've presented the results, your discussion, you first want to summarize the evidence, summarize the main findings, including the strength of evidence for each main outcome, and consider their relevance to key groups, e.g. providers, users, policymakers. Limitations, what are the limitations of the study and outcome level, e.g. risk of bias, and at the review level, e.g. incomplete retrieval of identified research, reporting bias. And then what are the conclusions? A general interpretation of the results in the context of other evidence and implications for future research. And then finally, what's the funding? What are the sources of funding for the review and other support for getting data, and the role of funders in the systematic? Okay, so that is a fairly good summary of what we just talked about today. And so these are the things that if you're reading a systematic review, you want to be looking for. Right? You want to make sure that people have done this. And if they haven't, I mean, if you get into the realm of reviewing papers for journals, these are the kinds of things you want to call the authors on and make sure that they've included if they haven't. And again, the basic two principles here are reproducibility and replicability. You want to make sure that you can reproduce their results and that their results are valid. Okay, so this is just kind of a quick summary of what goes into these sections. And so you want to include in your methods everything that people would need to be able to figure out what you did and why you did it. So what was your objective? Where did you get your data? How did you search? What were the limits on your search? For example, I only searched the English studies, or I only searched studies in years, or I only used these databases. How you selected studies, how you extracted them, and how you synthesized them. Now, here's an example of a forest plot without a meta-analysis here, right? So this is kind of a mixture of a qualitative and a quantitative summary. We've actually given the results for each study, but we didn't feel somehow that they could be combined for whatever reason. So this was a study that was done when I was at Tufts, and so you can see these particular studies are looking at a treatment for preventing atrial fibrillation, and there were two treatments, WACA and PVI, and to the left of one favors WACA, and to the right favors PVI. You can see the estimates from each study, and so 3 of the studies are basically favoring WACA, 1 is favoring PVI, and 1 is kind of inconclusive. And so the authors here, I guess, felt that a single number summary didn't really make sense because presumably there were enough differences in these studies, but they felt that some of these differences were due to study effects, but they also didn't feel that there was enough data to do any kind of subgroup analysis. So they ended up just presenting the forest plot without actually doing a meta-analysis. Right? So the summary here might be that 3 studies favored one treatment, 1 study favored the other treatment, and the other study was inconclusive. And then in the discussion section, you're going to actually summarize, interpret, compare, generalize, speculate, critique, itemize. You're going to basically kind of take, all right, what do I draw from all these conclusions, right? So this is the discussion section of any papers like this. But here, because you're summarizing evidence that's already out there and that people already know about, you're trying to synthesize it. You're trying to bring it together and say, okay, here is why I think these results. So your introduction might have said, the reason I'm doing this meta-analysis is because it's unclear whether this treatment is better than this treatment because the studies have been inconclusive. So now you're going to, in your summary, you're going to say, what you conclude. Do you still think it's inconclusive, or have you decided there actually is one preferred to the other, and what that's based on, and what are some of the possible reasons why those conclusions may be invalid, right? Why it may not be that the studies that those conclusions you've drawn might be right, because it's possible that there are all these particular biases that could change the results. Or I did this sensitivity analysis and my conclusion differs, therefore I'm not really sure about this, and I'm putting this out there as a possibility, but there's not a lot of strong evidence. So the evidence may be fairly weak for the conclusion to draw. And then try to generalize this to other populations. For example, if all the studies were done in the United States, does this apply anywhere other than the States? And what might lead you to believe it does? Right? Okay, so the final thing here is this is what we were trying to do in the course. And so I hope that we have at least met some of these objectives. So you can understand now why you need and how you can use systematic reviews and meta-analyses. You understand how a systematic review is done and some of the methodologies that are used at each step. Hopefully you can now better read and interpret evidence and these types of studies to support decision making in whatever field you're dealing with, or whatever area that you're trying to learn about. And with additional support, you could actually maybe undertake a systematic review. I know some of you are doing that, and you might not be able to do the meta-analysis yet without tomorrow's course, but hopefully you at least kind of know some of the principles behind systematic review and you know, what tools are out there and what you can do further. So let me stop there and see if there are any questions. I think this is the last slide, or maybe there's one more that says thank you. So these are a couple references. So I can certainly provide more, but these are free. So the first one I worked on when I was 2 years ago, the Institute of Medicine came up with this book, little booklet on standards for systematic reviews. And so it's kind of it's a little bit like the PRISMA checklist, but it's kind of a long document that explains kind of what a systematic review is and how it should be done properly. And then the Cochrane Handbook is a very good reference as well, even if you're not doing healthcare. It's got a lot of good stuff in there, and it's being updated currently, but that's the website for the Cochrane Handbook. So I think the new version is supposed to be coming out later this year. And this is the original one. You can actually get a hardback of this if you want, a paper copy, but you can also just get it on the web. And it is tailored toward the Cochrane collaboration, and so they do have kind of Cochrane ways of doing things, but most of these principles are fairly standard, and so useful. And I know the new edition has got a lot of new stuff, like on the network meta-analysis and some of these new risk bias tools. So hopefully that will be good. So any questions? How many people are back here? So hopefully I'll have a voice at that point. Okay.
I just thought I'd get up again since you missed me. Thank you again for completing the yellow form. There's no incorrect answer. I would appreciate factual answer at the top, but just whatever you have to share is appreciated, and also by the co-sponsors, some of who are in the room. Thank you. Due tomorrow, I'm to tell you again, we're not supposed to